Good day, and you're most welcome to today's technical session. I'm Ian Cowan. Technical session of the CNPS, which we hold on Saturdays. I moderate the Saturday sessions every second week, actually. And today we're very happy to have back, because he has spoken to us on a previous occasion, Frédéric Lassiaille. I think my French pronunciation probably isn't too poor. Well, ladies and gentlemen, the whole question of things like dark matter and dark energy have been sort of curious inventions to many of us dissidents. In fact, I think some of us would say that they are sort of ad hoc introductions to try to save existing theories, like, say, general relativity. Now, one of Frédéric's analyses has been looking at alternatives to the postulation of dark matter. And his system is called surrounding. Well, he'll explain to you better than I can what that is all about. But basically, surrounding seems to be an alternative theory to dark matter. And he says it is a modification of Newton's law, actually. So basically, with the model, with this particular model, the gravitational force is roughly inversely proportional to mass density at the location where the force is applied. And after presentation of the model, its dynamic is quickly applied to cosmology and astrophysics. So I'm sure Frédéric will be going into that in a little more detail during the talk today. The result is that a solution is given to 10 of the most important gravitational mysteries of today in a straightforward manner. Now, I'm sure that's going to get all of us to prick up our ears. There are a lot of mysteries with regard to today's cosmology, and the orthodox people seem to be just either dismissing them or introducing ad hoc hypotheses. So if Frédéric has very specific solutions to those, I think we're all ears. As usual, I'm proposing to deal with any very specific questions that the Facebook or YouTube participants pose into our comments. And I would ask you, well, as I say, I've no objection to your talking between yourselves, but if you do want specific questions addressed by Frédéric, please just put, this is a question for Frédéric, or maybe Ian, please note this, because otherwise I might miss it. But if you wish to discuss between yourselves, fine. And if I appear to be ignoring it, just that I'm giving you every opportunity to do that and praising you for doing it. But it's not something that we'll be dealing with. But having dealt with any specific questions, we'll then get to the more detailed discussion. So people coming in the green room, I think maybe later we'll have more people coming in the green room. We have a gentleman I haven't actually had occasion to speak to before. I think Ravindra Mundase, if I'm pronouncing his name correctly. Oh, there he is. So at least I've got his video. He's mute at the moment. But Ravindra and other people, after Frédéric's lecture and after the direct questions have been addressed, we'll bring people up. So I'm hoping you will contribute to the talk later on. So Frédéric, I'm bringing you up, and I'm going to give you the opportunity of addressing us without my interruption. Now, the only thing we have to do is, unfortunately, we didn't have an opportunity in the last 5 or 10 minutes to bring up your slides. I think you said you have 60 slides. You've obviously been doing a lot of work. So would you like, maybe you've done it. You're ahead of me, sir. You're ahead of me. There are your slides. So you've done it. You're a wizard. So what I'm going to do, Frédéric, is I'm going to bring myself down. You will have the entire floor. You might like to say a thing or two about yourself before we start, because I know you have spoken to us before, but perhaps not everybody who is in attendance today attended your last lecture. And what I'll do, again, with your permission, is I'll minimize your photograph so that your slides fill the entire screen, but you will still be audible. And if there are any problems, just call me and I'll come back. So, okay. So I'm going now. And I'm going to give you the complete.
Okay, it doesn't work as far as I would like it to. Maybe. Okay, 1 moment. I have to share my presentation first because I'd like to make it work before anything. Okay. Okay, so my name is Frédéric Lassiaille, and I have been searching. I've been working in physics for 2 decades, more than 2 decades. Now I have some background in mathematics as an engineer and also as a professor of mathematics. I have got also background in physics because of my research work, and I am a theoretical independent researcher, and very proud to be like that. So, what more? Maybe we can start with the presentation. So this is the start of the presentation. Can you see it? It's the image of a gas in green. Can you see it? Jan, can you see the presentation? I hope.
I can see it perfectly. Just some comments here about. Well, I put the thing on maximum size, but you have some thumbnails, and particularly those things on the right-hand side. Maybe if you can get rid of those, you'll maximize the screen. But I'll leave that up to you. Anyway, we can hear you perfectly and see you, Frédéric.
Okay, is it fine about the screen? I don't know.
Do you see those things? You have thumbnails on the left-hand side, which are your slides in very small, very small size. And then on the right-hand side, you have sort of formatting. Okay. What type of format you want.
I know.
If you can get rid of those.
No, that's because I have two execution of the same thing. So I have to start it all again from. Okay, it was a mistake from myself. Please forgive me.
If you need them, keep them. But it would be a bit easier for us.
No. I have to put it all screen, of course. It was a mistake. Sorry for that. So maybe you can see it.
So your slides have gone down. Why is that? Have you taken them down? I don't see them here.
1 minute. I have to just share again. Again the presentation. It was a mistake. Sorry. So I got to share once again here. Share the screen.
So you have to click share entire screen, and then click the rectangle. You've done this already, but you have to. Yeah, here it is.
Here it is in full screen now.
Well, I'm going to maximize that, but you haven't got rid of the certainly the formats on the right-hand side. Is there a little X up there? Yeah, exactly.
Yeah,
perfect.
Perfect.
Perfect. I'm not too fussy about the thumbnails. If you want to keep those, that's fine. I'm going to maximize that now, Fred.
Okay. So the first slide, I don't know if you see the same thing as me. The first slide is showing a cloud, a green cloud. Can you see it?
Yes, no, yes.
Okay.
Cliquez pour ajouter un texte. So
yes, of course.
So, okay, but apart from that, it's surrounding.
Okay, so it is an AC molecular cloud of Spicer Space Telescope NASA. It's written down on the slide. Okay. And okay, this is an image for what I call sounding, which is my gravitational model. This image is put here because it's a good illustration of what surrounding is doing. Surrounding is calculating gravity force, by using all the surrounding matter, all the surrounding energy, which is around the location where we want to calculate the gravitational force. The table of content of the presentation will be this, quite different topics. So, of course, the main part is here about the model itself, the surrounding model. Then we will see the behavior of the model, some quick showing of the caveats and limitations, if there are. Also, a specific slide here about criticizing relativity. It's a good thing to criticize relativity, really. So, and going back to surrounding, explaining why it is a gravity modeled as predicted by relativity. A comparison of this surrounding model with dark matter and the lambda CDM model, and the conclusion. So the introduction is about this model, which were created in 2015. It's an alternative to dark matter, as Ian said to us in the introduction. It's a modification of Newton's law. So what is the main principle of this gravitational model? The main principle of this model is the surrounding effect here. Surrounding effect. It's very, very simple. As I said before, the gravitational force is inversely proportional to the surrounding energy at the location where the force is exerted. That's something I've been already saying 2 minutes ago, but except that here is more precise. So surrounding was designed to express this effect in the simplest possible way. Let's see how it works more with a picture. This is the regular Newton's law. You regard the attracting object here. And here is the location where we want to calculate the F force, which is a gravitational force attracting us when we are here, attracting us to this object. So this is a regular formula, except that it misses maybe some minus sign, also, but it's a matter of convention. And with this, it still remains gravitational mysteries. Okay, as everybody knows. So now the modification which is done by the gravitational model, which is called surrounding, is the following. We consider the surrounding energy around the attracted location here. We calculate the value of this energy, which is located here, except the mass, eventual mass of the particle. And we insert in the equation a multiplying factor, which is using this value here in the denominator. In the numerator, there is a constant, which is, of course, the surrounding energy value valid in the solar system, in such a way that when you are in the solar system, you will retrieve usual Newton's law. Okay. With this new equation, this is a surrounding model. It solves. Sorry for that. It solves. It's a long time to go back. Okay, sorry. It solves the gravitational mysteries, as we will see. I didn't work on all the gravitational existing, all the existing gravitational mysteries, of course, since I am alone and since it's a huge work. So I've been working maybe about 10 of them, the most important one. And the result is really, really strong. May I say that? Okay. So this is the motivation. Yes. Okay. Sorry. So this is another thing. This can be seen as a motivation. In fact, surrounding is a standalone gravitational model. It doesn't mean anything, doesn't need anything to exist. Nevertheless, it is the behavior surrounding a gravitational model is the correct behavior of relativity. Because as I wrote here, relativity has been proven to predict a variable g. This was the main point of my January presentation here in the CNPS.
Frédéric, please forgive me for interrupting. We just have a couple of comments here. I've looked at myself. We're only seeing one slide, which is the one with the green base. We don't see any other slide. We don't see any other equations. Were you progressing?
Oh, okay, so this is very bad. This is very bad. This is very, very bad. I don't know what is going on. Okay, because I shared. Okay, maybe I have to share my screen. It will be. But the problem is that I cannot share my screen, my whole desk, because it's green. The button is green when I want to do so. That's the problem.
But if that's one slide, and then you have slide 2, 3, 4, 5, 6, can you not advance maybe just with the up and down arrows?
That's how I'm doing.
You seem to
I
be
am
stuck
doing
on the
that.
first slide.
I cannot share. Okay, maybe this way. Okay, I didn't click on it. That's why.
Okay.
Probably.
Okay, we'll try again.
I had to click on the image of the screen before. Okay, sorry. Maybe it's better here. Hope so. I cannot see it.
Okay, we have your screen now. Yeah, you have to click probably about twice or 3 times. We have your screen now, so whatever you put up, we'll be able to see.
Okay. So that's why I started all again. Sorry for this big mistake. So,
thanks very much.
We ought to do that before. Sorry for that.
I hesitated to interrupt you, but I'm glad we did now.
Sorry about that. Can you see it in the? Oof, I don't have the way to. When I click on a full screen, it doesn't work. Sorry for that. Présentation.
Don't worry about that. I've maximized the screen here, but by getting rid of your photograph, your video,
okay.
but we can still hear you perfectly.
Okay. Can you see the text surrounding here?
Yes.
Okay. Can you see table of content?
Yes.
Okay. So I'll go back quickly. So this is table of content. Okay. I don't want to go back to it. I saw it. I've been describing by voice. So it started in the 15. Okay, so I was talking about that. So this was Newton's law. I have to show it again. It was not shown, in fact. So this is a attracted location where we want to calculate F. This is Newton's law. And this is the attracting object, which attracts us, and which makes this force here. Okay? With this Newton's law here, there are still gravitational mysteries. Now, with surrounding, we use surrounding energy around the location where we want to calculate F. We put this value in the denominator of another term, which is a factor here, and above is the numerator, of course, the constant is, of course, the surrounding energy valid in the solar system, in such a way that when you are in the solar system, you retrieve Newton's law. With this new equation, you got what I call the surrounding model, and most of the main gravitational mysteries are solved. That's what we want to do. That's what I want to show you today, if possible. So this is the motivation of This is a mathematical motivation, in fact. In January, in my last presentation here with the CNPS, thanks to Ian and all the staff, I've been presenting this, the fact that relativity has been proven to predict a variable G. This is done in a 50 pages document available on my blog. Here, you can see, you can check my blog. You can Google me and find my blog very easily. This new relativity follows the rule of the surrounding effect. So that's the main motivation of this gravitational model. Even though surrounding gravitational model is a model completely standalone, it doesn't mean it doesn't need anything. Okay, this is the equation of this new relativity, in which it's quite easy to deduce. After 2 lines, you deduce the surrounding effect. Because you take this total energy of d mu here, you pass it from left to right, and it is exactly your surrounding value. The problem is that with that equation, it is that it's not very much practical. You know, it's fundamental relativity, and it misses the exact knowledge of this attenuation function here. Sorry for that. So that's why here I prefer to modelize this surrounding effect in the simplest way possible, which is this gravitational model, and which is this factor I just showed you before. This inserted factor in front of Newton's inside of Newton's law. Okay. So this is what I've been telling. The mathematical demonstration demonstrates prove that relativity is working with the variable G. Of course, in fact, I should say, why using such an anthropocentric value of G? And from it, but this is a real mathematical demonstration. And from it, it comes the surrounding gravitational model, which solves many of the main gravitational problems. This is the research I've been doing for 20 years. So you recall the same part here. You have something to say about particle physics. I told you about that in last January. And you have also many things to say about the test of the model. I will focus today only on that part, of course, here, surrounding model. So this is the history of the model. I don't go into full detail of it. It was published in 2018 in the APG, which is a proceeding of the conference. This is, as I said to you, this is a famous vector which is inserted in the Newton's potential. It's the same thing, inserting it in the Newton's potential, or quite the same thing, or in the force itself. More fundamentally, it's better to do it here. So you can find here what represents the surrounding value. So you have a constant here, which is alpha. You have the matter density, which is calculated in the sphere. You remember there was a sphere around the location. And here, rho u is the matter density of the universe at the time of the measurement. Of course, it goes into a relativistic formulation. So you don't have to be so proud of those kind of calculations. And the Lagrangian, of course, same way. So those are simply translating what I've been talking before. You see, relativity is something very hard to understand, complex, but after all, it's only a framework, a mathematical framework. Here, the main important part of in physics does not lie really in relativity. In fact, in some way. Not in some way. Talking about the surrounding gravitational model, the main part is about Newton's law, exactly what I've been doing before. That is, you insert a multiplying factor. That's all. So therefore, this is not this is not something so much interesting for the gravitational model of surrounding, even though it's very much correct. Of course, I'm very confident about those equations. It's not that. Okay. So what is the behavior of the model? First of all, the famous Virial theorem, you know, the Zwicky problem of the clusters of galaxies in which gravity is 5 times greater than what we know. It's immediately solved here very easily, because AGM matter density, of course, is not the same. It is not the same as this term here, which is a corresponding term valid in the solar system. It makes 5 times. Of course, I've been fitting the alpha parameter, and I've been fitting in some way. In fact, I didn't finish very much. All I fit was alpha here, which gets 2 values. One value is inside of galaxy, alpha 0. And another value is when we are outside of any galaxy. So you get only 2 values for it. And it's always a constant. It's always the same constant throughout the universe. Therefore, it works extremely well. It's not very much fitted. So about galaxies, first of all, of course, the main problem of gravitation of today, which is the split profiles. This is reality. I don't have to explain. I think most of you understand what we are talking about here. Okay, and this is a simulation of the surrounding model, a simulation using a very simple n-body problem. Simulated galaxies. So one word about this simulation. Sorry, going back. One word about this simulation. It's important. When you do simulations for physics, you really have to describe what is exactly doing your program. I don't know if it's so often done by the mainstream community. It's extremely important. This has been done, for example, in 1971 by Professor Hall, if I remember well. I know it because I wrote exactly the same program as him, except that he was doing a very huge thing for his time, 1971. So this program, he make it work in a big room, a big computer of the size of a big room, of course. And I've been trying to do. No, I've done it on my PC, of course, exactly the same program, which is extremely precisely described. So what is doing this program has been described by Dr. Hall in 1971, very precisely. This was a very good job, a very scientific job. So exactly the same thing, very, very simple, a toy and body problem. Maybe I took 1 million galaxies. I don't remember the number, sorry for that. But okay, you can retrieve my programs. It's available on internet, on my blog. So okay, so it's very easy, and I don't mix it with anything. I made it as simple as possible. It's very important. This is very important to deal with very simple programs. This is very funny because when I simulate my first galaxy, I saw this stuff here. So I said to myself, so there is a bug somewhere. So I've been searching for this bug for maybe 1 day or half a day or 1 day. Hopefully not more, because at some point it reminded me something. So I searched on the internet, and then I saw this stuff here. Then I say, wow, this is working much more than I thought. This is a funny story. So, okay, so let's go. So this is, now let's go to the real simulation, executing simulations. Of course, it's a selected simulation. So maybe one of the best of the one I got. First thing you have to simulate. Sorry, you have to simulate surrounding. This is a simulation of the speed profiles of surrounding. So it begins with Newton's law, and the surrounding is slowly added to the simulation, and then you retrieve exactly what I was talking about, which is a flat speed profile, except that it's very much there are plenty of up and down, and it's varying very much. But this is, for me, I'm not an expert, but I think it's a very good thing to have this variation. Another, everybody knows this is Newton's law. Okay, so by comparison, of course, it's also always the same program here. What has been modified is only the model, the simulated model. Of course, it's changing. So let's go back to the structure of a galaxy. Now the same simulation, two surrounding, but watching the structure of the galaxy. So this is really astonishing. I can't say anything else. Sorry. So you got everything. You got the rotating bar, the fast rotating bar. Around it, you got the spiral arms. You got many dwarf galaxies, and at the end, a ring galaxy. It's like a real dream. You can't dream of something more precise than this, or something more compatible with experimental data. For comparison, the same program, but simulating only Newton's law, what you get the usual pizza of Newton's law. Okay, so this is incredibly astonishing. Now, with the bullet cluster, this is a famous image of the bullet cluster. The problem is solved in a very simple way also. You just have to calculate the potential of the attracting gas. So I'm talking here only of the gas. So I forget the stars, the galaxies. I get only the gas. I consider the gas. Okay. And the potential of this gas is calculated as usual by the Newton's law equation here in the continuous formulation, which is a convolution. You have here the support of the gravitational model, G divided by the distance, and here matter density. And it results, normally, if you don't have this, if you don't have the denominator, you get the potential of the Newton's law potential of the gas. Here with surrounding, you have to divide with another convolution, which is quite the same convolution, except that this support here function is replaced by another one, which is a heavy side. A heavy side, it's more the double heavy side. Sorry, it's a door function like this. It's a door function. Okay, because you have to calculate the surrounding, which is the surrounding value, which is around the location. The fact is that for gas, which is a gas, a bullet cluster, which is homogeneous, and for which the matter density does not evolve very much, it stays roughly constant. The matter density of gas evolves very slowly. Because of this slow evolution, the effect of the support functions are very close to each other. So those values are very close to each other. So it makes one. Oh, sorry, not one. It makes something constant. Not one. because they are not the same. They are evolving. The values are evolving very slowly, but the support here are very similar. So the result is a constant. As far as the matter density evolves slowly. There are exceptions to that. At some edges of the gas, you can here it is predicted how we say this, up and down. There are up and down which are predicted when the matter density evolves quickly. And interestingly enough, this is exactly what we see in some images of the Bellot cluster. This is a 3D comparison between Newton's law and surrounding, where we can see that it's really solving the problem, really. So the peculiar up and down I was talking about are here, and somewhere here. It's retrieved by your surrounding also, those peculiar things. It's explained by the peculiar behavior of the convoluting function. Now, this figure, as everybody knows, is representing the large scale problem. Heterogeneity, of large scale structures. I don't address the small scale structure. So for this problem, it's as usual, it's completely astonishing. The model is solving the problem in an astonishing manner. Let's go at it. There are two things to say. First thing, in a void, gravity is increased by a factor of 40, which is huge, which is used. The result, physically, is that the matter is completely wiped out of the void. So it makes the voids completely empty. Second thing, when you calculate matter density more precisely, in a situation in a matter density which were one dimension only. Here you got only one wall here, another wall here, and you want to calculate matter density in its stable equilibrium. If there is one. The answer is yes, there is a stable equilibrium. There is an equilibrium first. Is there an equilibrium? Yes, there is an equilibrium, and it's like that. Complete void, and then an equation like this to retrieve the whole matter density. Complete void here, 0. First thing. Second thing, so it's not now, it's a third thing. In fact, the second point is divided into 2 points, which is there is an equilibrium, it's this one. And the second point of here is that this equilibrium is a stable equilibrium. Incredibly well solved. You cannot have anything like this. So dark matter here, by the way, dark matter is completely rolled out here. Newton's law is completely rolled out. It's a sinusoidal function, like this. And I'm afraid Mond is working. For me, it's not really maybe it's probably working quite well here. But we will go back about Mond later on. Cosmology. For sounding, the cosmology is very simple because there is a dividing mechanism. The same always dividing mechanism in which matter density which attracts is divided by itself, roughly speaking. Here it's not roughly speaking, by the way, it's exactly that. And you get a constant which is, of course, the fine-tuning, the famous fine-tuning critical matter density of the universe. So therefore, a de Sitter universe is predicted, which gives an explanation for the fine-tuning issue, of course. The space coverture is equal to 0, which is, of course, predicted here. The deceleration parameter is exactly Q equal to -1. So I had the remark of someday of some physicist, a mainstream physicist, who told me, yes, it was when I was submitting my paper, who told me that in fact the measured value is not exactly -1, it's minus 0.9 or something. Okay, so it was just for an anecdotic remark here. So, okay, this is cosmology because of this equation before. The time since last scattering is 100 gigayear. It's a huge, 7 times greater than with lambda CDM. As such, it allows to understand the existence of IZ clusters, which were already a problem in 2018. It allows the existence of many big giant galaxies, such as this one. It's not the only one like that, which has a very big diameter, and for which simulation shows very, very obviously that it's not enough. It's not enough. 13 billion years. It's not enough for such a galaxy to exist. These were already rolling out dark matter in 2018. Now with the James Webb Telescope, it's even more those galaxies and those clusters. Here you got galaxies which are quite big, in fact, and they got some only 300 million years. This is completely out. And the cluster here is very interesting here, this one. It's a 6 sigma incompatibility with the LCDM. Yes, because of not so much because of its edge, but also because of its dynamic. So therefore, the lambda CDM model requires increasingly absurd assumptions to explain recent observations. Other addressed mysteries, other addressed mysteries, which I don't have time to go into. The low matter density environments in surrounding is a very big topic in front of experimental data. For example, it exists very big galaxies which are inside of voids. And what is weird is there are many things weird, but one thing here is that it's still existing in this this void. But this stability is very well explained by surrounding, because in a void, the surrounding value is very low in the border, in the outskirts of the galaxy. Therefore, it enforces very much the stability of this galaxy. Also, there is a big topic with dwarf galaxies, in particular when comparing with MOND, because MOND here is not very. The last thing that we can say is that it's not working very well. And here, dwarf galaxies, even the faint one, for the same reasons as before, the dwarf galaxies are very much stable as far as they are lying in an environment with a very low matter density, which is often the case, probably when you talk about faint dwarf galaxies. Okay, if you talk about a faint dwarf galaxy, of course, you can suppose that the surrounding of this galaxy is very low, is very weak. So it increases very much gravitation, and it increases stability of these faint dwarf galaxies, galaxy alignments in cluster, etc. No time to go into that. So there were remaining mysteries in the 2018 version. It's 18 here. In 18, there was this problem. Today it's solved. I don't have time to write the second version, taking this into account, because I'm working on relativity. correction of relativity, but it's really solved. I've been doing big work on it. You just have to modify surrounding slightly by making the size of the surrounding sphere variable. Okay, same thing here for the dwarf galaxies. It solves the same way. And this, yes, I have to work on it also a little bit. Okay, of course, it remains works to do. Caveats and limitations of the surrounding model. Let's see it. Violation of momentum conservation at large scale. Yes, of course, you can imagine that since you add here on A location, you add a surrounding value which is not the same as in B location. So therefore, there is violation of momentum conservation. But in fact, when you, that's a funny thing. That's really a funny thing. But in fact, when you really think on that topic, you realize that it is exactly the opposite which is occurring. With Newton's law, there is a violation of momentum conservation. See, it's with Newton's law that you get it. Why? Because you don't take into account the surrounding. You have to take into account the surrounding in Newton's law in order to see to check if there is a violation. In fact, there is not. But okay, it's a quite a little bit discussion here. But in fact, the conclusion is that there is no violation, in fact, at all, because you have to take the surrounding. You get to take the whole energy we are talking about in the laboratory in order to predict what is going on in your laboratory. If you only take A and B particles and there is surrounding around them, you get a wrong result. Okay, so let's go quickly. The time since last quartering, 100 gigayear. Yes, sometimes I saw people in my conferences, the conference to which I participated, I saw people opening their eyes like that, 100 gigayears. Yes, but please refer to James Webb Telescope discoveries. This nucleosynthesis. So this is a real good remark. I got this remark, I must say, after submitting to some interesting journal. Okay, so for this, but the answer is very easy. Of course, surrounding is dealing only with gravitation. It's not dealing with the radiation era, the radiation phase. As I said to you, Q equal to -1 is not good. Oh, okay, so that's make me laugh. That's really make me laugh. Quite nothing to say more than that. It's not a caveat. This is okay. Nucleosynthesis and the alpha parameter are the only caveats. But for the alpha parameter, it gets only 2 values, as I said. So okay, I had questions about it. I have also a bit work to do here about the alpha parameter because I have shown something occurring in the galaxy, in the experimental data of the galaxy, etc. I don't have time to go into that. So let's talk a little bit. I will try to now to talk a little bit about the job of criticizing relativity. On that job, I must say I am the first one to make mistake. Really. I've been searching for 20 years, more than 20 years, how to criticize relativity. This is the good approach to physics, in fact. That's why I really have to show myself humble on that topic here. So I know that in NPS, it's always very oftenly done. It's a good thing to be done. First of all, about general relativity. In fact, curiously enough, it's an easy task to do with general relativity. There are several side caveats of GR. It's quite well known, even in the mainstream. Some of them are listed in my articles. But now, criticizing restricted relativity is another task. For me, from my point of view, it's extremely hard to do. I've been doing so for more than 20 years, it's extremely hard. You have to be aware not to say nonsense. I'm talking to myself here. Okay, I'm not talking to you very much, as much to myself. Really, it's much more tricky than what may appear at first glance. It takes, but if you do it correctly and enough, at the end, it's extremely fruitful to do, because the criticism of the current explanations of the twin paradox, the result of this criticism is that you obtain the surrounding effect, you realize the existence of the surrounding effect in relativity by criticizing the twin paradox. And you realize that a chapter, a small chapter, but a chapter is missing in relativity. And at the end, you get exactly my work, in fact. So you can see my work as starting here. You start with the twin paradox. One word about it. One word. So the twin paradox is very interesting, because in the literature, you cannot find the most important remark, which is why this twin, which is staying on Earth, is the older. Why is it the older? Why is he the older? Because so the answer, implicit answer oftenly is, because it's attached to Earth, which is attached to the universe. Dot. And return to the line. No, it's not the end. It is the beginning. Why is it that the universe makes a difference? That is a very good question. You have to say it. Because the universe is the biggest. It's so simple. So it's completely dismissed in the literature. This is a real explanation of the twin paradox. The twin which is attached to the bigger energy will be we have the time lasting the most. That's all. That's the explanation. That's the correct explanation. And when you go in details in that explanation, you will really quickly find the surrounding effect, in fact. So surrounding a gravity modeled as predicted by relativity. So we are in the same kind of discussion. I go back to what I was talking before. There is a link between what I presented on January, which is my work on relativity, and also this surrounding gravitational model. This surrounding gravitational model is inspired very much by this corrected relativity. So this is a slide that I showed you before, mathematical demonstration showing that relativity predicts a variable g. From it, you get a surrounding effect. You get a surrounding effect. So I write a very simple gravitational model expressing this surrounding effect, which I call surrounding. When working on it, it solves very easily in a striking manner most of every gravitational mysteries I've been working on, except that I didn't time to work on all of them, on each of them. Sorry. So, gravity model as predicted by relativity. A small chapter of relativity which has been missed from the start, which deals about the first degree of derivation link between matter and space-time structure. Maybe you cannot see immediately the link, this phrase, the link between this sentence here and what I was talking about 30 seconds ago about the twin paradox. But it's the same thing, in fact. Please go to my 50 pages. I'm sorry. You don't have to read the 50 pages. Please only read the 20 pages. There are 30 pages of appendix, 30 pages of appendix. So, and also there is I will show you, there is a resume, synthesis. Okay, so now, from it, writing the beginning of this chapter, G constant is not proven to be a variable, and the surrounding effect appears in relativity. This is the demonstration I was talking about. So you have a prerequisite, and then you watch what is going on exactly, really, when you have a complete vacuum. When you have complete vacuum in space-time, you insert in this vacuum, you insert a particle. It does not behave as the literature say. That's obvious to me now. It produces a singularity everywhere in space-time. Why? Because it's vacuum. Simply, it's vacuum. Okay, so I have another argument for that, but I prove this here in this paper. So this is a very big difference with what today's relativity predicts. Today's relativity predicts that in vacuum, a particle generates a space-time deformation, which is exactly corresponding to Newton's law. With this correction, it is still valid, except that the effect is infinite. There is a singularity everywhere. So that's the only thing. But it makes a huge difference. And then when you see what is going on for a countable number of particles, you retrieve quite easily the equation between energy, another equation between energy and space-time structure, except that this equation is dealing with the first degree of derivation. Otherwise, you know that Einstein equation is a link between those two, but using only the second degree of derivation. Then the second degree effect is predicted, and an equation of G is given. An equation of G is given, obeying to the same surrounding effect, of course. Now, let's compare a little bit the surrounding model to the only really existing model of today, which are dark matter, Lassiaille, and MOND. So I've been putting here an array. On the left, you got the topic. Here, lambda CDM and dark matter and dark energy, and MOND here, and surrounding. So in bold here are the problematic things. You also see here many problematic things here. Rolling out, problematic, grotesque here. Fine-tuning is really grotesque with lambda CDM. Edge of your universe, as I said before, is really grotesque. MOND is very well working in front of it. MOND is working very well. And surrounding, okay. I'm sorry, but I didn't find anything really even problematic. I'm sorry to say that, really. It works extremely well. General remarks on the model. So lambda CDM, several anomalies, Tully-Fisher law, bullet cluster. The model is fundamentally flawed on certain issues, such as recent James Webb Telescope observations. Today's development is simply grotesque. Despite a century of research, DM and DE, dark matter and dark energy, have never been directly observed, particularly in laboratory settings. This is something I've been listening in a conference. It was in 2011 in Baltimore. A mainstream physicist told everybody that dark matter, he was talking only about dark matter, have never been observed in laboratory settings. Okay, I don't remember the name of this famous guy. 2011. MOND. While MOND resolves several problems, it fails in broader areas such as Lassiaille structure, etc. For me, MOND is working very well. Nevertheless, here it's based on purely. The problem for me is more here. It's based on a purely experimental phenomenological equation, like the Fizeau equation. Maybe somebody don't know. You don't know what is a Fizeau equation? It's the equation of the composition of velocities. When you have water, you have a light in water, and you make the water in motion, and it retrieves more or less a composition of speeds, which is a relativistic composition of speed. Okay, in the laboratory, when they have done this, they didn't know very much relativity, so they made a phenomenological equation in order to express with the equation what is going on. How the speed of light evolves when the speed of the water is increased. Okay, the final speed of light, of course. And at the end, of course, it was the composition of speed of relativity, in fact, the correct equation. And there is a link between this relativity equation and the Fizeau equation. The Fizeau equation being an approximation of the first one. Okay, so it's a phenomenological equation. And also, one word, for me, the most important thing is this one. It's the prediction of monde are quite good because the underlying mechanism is close to the surrounding mechanism. I can say this in one sentence. Monde, let me remind that monde predicts that when acceleration is low, is weak, then it obeys to the 1/r law. And when it's strong, it obeys to the usual Newton's law, which is 1/r square. Sorry. But the thing is, when acceleration is low, most of the time, the surrounding value is also low, of course. Most of you can assume it's not an assumption. It's quite obvious, roughly speaking. When you have inversely, so it's true also. When the surrounding is low, it means that there is a very weak matter density everywhere. Of course, acceleration is supposed to be very low also, as low, sorry. So those two mechanisms are based on quite the same data, in fact, or data which are correlated. So the two gravitational models, which are monde and surrounding, are based on data which are correlated each other. So it explains why monde was working so well before. So that's why also I am not so much against monde, you see. That's for me. And also it's a good news for monde because at the end of the 40 years of existence of monde, it shows that it was right, in fact. So surrounding, this model is extremely promising. It is still under development. It addresses several material issues. In fact, I have been working only on several major issues. Okay, but it requires significant further work in astrophysics to confirm solutions for topics like galaxy rotation speed and details and tidal phenomena. But this model is theoretically very well supported as it incorporates the full theory of relativity after adding the missing chapter. That's very important. That's the most important part. You cannot do a model without theoretical foundations. It is completely out. So what about the social context? One word about the social context. So there are two slides. The first slide is my publications, conferences, and collaborations. Publication, numerous submissions has been rejected by peer-reviewed journals. Although my submissions were rejected as timeless, this is true. I had the answer. Your paper is timeless. Well, so when I watched that, when I read that, I thought it was a mistake of my mail or something. Because when I translated it, I didn't understand. It was something like old-fashioned or something. I don't know. This highlights the challenge of pioneering research that does not follow trends, yet aims to shape the future of science. In fact, it should be exactly the contrary. The contrary should be the correct answer. Your article is very interesting because it's a pioneering research. That should be the answer. No, it's a contrary. It's a timeless. So you are timeless. Okay, thank you for that. Okay, so I didn't lose too much time about that. Trying submissions in peer-reviewed journals. are finally published in the EPG Web of Conferences following the ECNFP conference I've been doing in 2018 in Crete. And also Relativity Predicts the Variable G, which is another article. I wrote a very small version of it, which is a little bit deprecated now, but not so much. It's published in the proceedings of another conference, which is called IWNT. It's a nuclear theory conference. It's here, somewhere here, IWNT. Here, IWNT, it was 40 or 41, I don't remember. Okay, so over 20 participations, collaborations, occasional exchange with the Mont community, regular participation in this IWNT conferences, a single valuable collaboration. Okay, but okay, let's go further. Social context. So the social context is here. It's just a reminder. 90% of scientists prioritize job security. I don't have time to go in full detail of that. Scientific journals, supposedly of high repute, reject solid work, despite over 20 years of effort, and groundbreaking funding. Sorry for that, but it's really what you can see. You can just see it. It's so obvious. The simulations, yes, the simulations. Yes, I have information on that. Simulations like those for Dharmata are very often, sometimes, rigged to fit preconceived ideas, distorting scientific truth for decades. The least thing that we can say here, maybe it's too harsh here. The least thing that we can say is that it misses very much what is doing the program. When you put your research, your article on a simulation, you really have to detail completely what is exactly doing your simulation. I'm afraid this is not done all the time. Okay, this behavior here undermines true progress. My work, ignored for 2 decades, could very well represent the major discovery of the 21st century. Sorry for that. Okay. Maybe as I read it, I find it pretentious, but so that's why I have difficulties in reading it. Sorry for that. Okay, so conclusion. The only model solving hologravitational model anomalies. That's what we have been seeing. The other, Mond partial fits, no theoretical foundation, and lambda CDM is increasingly grotesque. Okay. Zero detection of dark matter. Grounded in relativity, no ad hoc fixes, a minimal physical extension of Newton and Einstein. Yes, it's only a small chapter in relativity which is missing, in which it turns out J is no longer constant. No tuning or in relativity, yes. In relativity, there is no tuning. There is a tuning for ground surrounding. Sorry, in surrounding, as I show you, there is the famous tuning of the alpha parameter, and also the current version of surrounding is not the end. It will have to be improved. I have already some good improvement of it. So it's wrong. Sorry here. Not doing. There is a slight tuning, very slight tuning, but it's a tuning. This isn't a patch. It's a shift. Sounding is the first current predictive and physically sounded gravitational. Yes, of course. It's the first physically sounded alternative gravitation. I think I showed you that. Maybe you can contradict. Of course, you have to contradict me very much. I'm respecting that. Also, a new chapter in gravity. Sorry, has begun. Okay, scientific merit, etc. So that's all we got for today. Thank you very much. You're here.
Okay, I'm coming back now. I think we can take down your slides just for the moment. If necessary, we can bring them back, Frédéric. Well, thank you so much for that exposition. It follows very, very well from your earlier presentation last January. And I'm looking actually. I think today we haven't had many participants, or certainly many comments coming in on the social media. So I think we'll be able to devote practically all the time left to us to the participants in the green room. So maybe just one or two points before we get to that. So yeah, it appears that you're comparing the conventional lambda CDM model, the MOND model, the modified Newtonian, and your own surrounding, and you're finding actually that the surrounding seems to be achieving quite a degree of concurrence with experimental results, which some of the others, certainly not the lambda CDM, can match. Your experience in regard to trying to get things published and so on, I think mirrors what quite a number of us in the CNPS, including myself, for example, have experienced. And I don't know personally who the editorial person or persons was or were who used the words which puzzled you, like timeless and out of vogue. I mean, timeless would seem to connote to me valid for all time, and out of vogue is a thing which one wouldn't use. Out of fashion. It seems quite odd that they use those terms. I don't understand that at all.
Sorry, is it the correct translation, old-fashioned for timeless?
Old-fashioned for timeless? No. It sounds
what is the
like
correct translation?
It sounds to me like a person just taking there's no timeless or something, or out of vogue.
I don't have time for you.
No,
I don't have time for you.
The idiom would be if you made a very good comment. Let's forget about scientific theories for the moment. A very good aphorism about human life. You'd say that's timeless. It's so marvelous that like what Socrates said about philosophy is timeless. It's so fundamental. It hasn't needed to be modified. Well, that's the way I would take it anyway. Maybe out of vogue might be old-fashioned, but it's a very strange set of words to be used in an analysis or a review of a paper. You know, what's in vogue this year is maybe the way ladies' hair fashions or men's shoes are. That's in vogue or out of vogue. So I don't know, when you put it into a translator and you got a French, you got a French relationship to old-fashioned, did you? That doesn't sound right to me.
Yeah, I also. No. Also, I put that also on GPT. On GPT, not far. I don't have it again. No, I cannot show you it. I don't remember. There was something interesting with GPT, but I don't remember.
Yeah, we have to look at that.
I don't understand this.
Very strange words to use. I would even go so far as to say that they probably were not put in by a native English speaker. Presumably, your paper was in English. And maybe just before coming to the discussion, just one further point. So you're talking about in the surrounding system, the force being inversely proportional to the mass density. Isn't that correct? Is that the reverse of the Newtonian system, where the force would be proportional to the mass density?
You have the two mechanisms at once at the same time. Can I go back to my slide, please?
Let me put it up.
No. Maybe I can show you.
Well, I think we might just have your screen there, so you'll have to
only
go back
one
to your
slide.
slide.
Sorry. Yes. Pop. Yes. Here. Can you see my presentation?
Again, now we only have
No,
the
you cannot
first
see
slide
it.
there surrounding.
No.
Okay, it's coming up now.
Here? Or maybe no.
Okay.
No. Do you have it?
I have it. Yeah,
Do
it's
you
a bit
have it?
small.
It's
I'll
written
leave
in
it for a
Newton's
moment.
law.
Yeah, 'cause we've seen it before. So that's the basic Newton law.
Okay. One moment.
So what's yours?
One moment.
Yeah.
Okay, what's the problem?
Yours
One
in
moment.
contradistinction
Okay.
to that.
Okay, so this is a Newton's law. Okay. One moment. Okay. So surrounding gravitational model, you insert a multiplying factor here.
Yeah.
It is this factor which obeys the law you were talking about. This factor is inversely proportional to the surrounding energy. But you had inserted it to Newton's law. So, as usual, the force is proportional to m, little m, and big M, of course.
Yeah. So that additional term actually doesn't cancel out the m's there. It's an additional term.
Yes, most of the time it does not cancel because m are particles. M is a particle. Let's say it's a planet, or it's more a planet. This is a planet also. So you've got m, big M, and around the location, matter density is not empty. Is not zero. You don't have complete vacuum. So you have the value here is not zero. It is not exactly M on neither big M.
Yeah.
But
Yeah.
sometimes, this is a very interesting topic because sometimes when everything is very homogeneous, it really cancels out. This here cancels one of those two here, depending of which one you are going, and that's what make surrounding works so well, because sometimes it cancels out.
Okay.
And
I think there's some discussion which I'll bring in now. For example, Ravindra has said general relativity is not proven. This is just another theory. So we might have a bit of a discussion on that, if that's all right, because
yes,
I think, if I'm not mistaken,
yes, of course.
Your ideas are consistent with an admittedly modified SRT and GRT. They don't fly in the face of it. I think you said, unless I misunderstand you, that you're incorporating a form of modern relativistic theory, suitably modified. So, whereas I think some of us might be more opposed to that. So, I'm just going to check if there are any comments before we just get to the.
Yes.
No. Okay. There are no questions for you, really. Just some comments. Okay. Some chap says bonjour, which I should have said earlier. Okay.
Bonjour.
So I always say good day, by the way, because we're in all different time zones. So I'm reluctant to say good morning or good afternoon. So you
Good
say
choice.
bonjour all the time, which is good day. So people have been coming into the green room, making comments and then disappearing, which isn't very nice. I wanted to invite. Well, our stalwart participant is James Keane, and he's still here, thankfully. He's made a number of comments, and I'm going to, if you'll forgive me, Jim, as usual, I'm going to impose upon you to raise some of the comments you've made yourself.
Okay. Well, thank
Yes,
you,
please.
Frédéric, for your presentation. Let's start with, how does relativity predict a variable g? This statement appears in your slides repeatedly. Should I repeat that, sir?
Yes, maybe can we just... No, how does relativity predict a variable g? That's a question?
Yes.
Is that correct?
Yes.
Is that the correct question? How does relativity predict a variable G?
Yes, that statement appears in,
Okay, so maybe if you
all
can
over the
see my
place in your
slides
slides.
here, can
Can you demonstrate how it does?
Yes, it was.
For example.
Oh yes, it's available on my blog. So you go on Google, you Google Frédéric Lassiaille by name, surname, and then you
let's
search for my blog.
simplify this.
I have a blog which is called
Is this
Site
variable
123.
G the Newton's constant? Is this variable G Newton's constant?
The universal gravitational constant you're calling G.
And
by the way, is this variable in your
there are
system?
silences in your phrase because of technical problems.
So I think, Jim, if I may come
maybe
in,
I don't.
Jim is asking G, uppercase G. That's the proportionality constant in Newton's force law that you just showed. G, and it's variable. Well, you're contending that it's variable in relativity theory, and you've discussed this on your blog, which maybe we can look at offline. But I have a further question, which I hope clarifies it a bit. Is the G, the proportionality constant, the gravitational constant, variable in your surrounding theory?
Oh yes, of course, yes.
Yeah, I think so.
That is what I am proving.
Does that answer that, Jim? I think Frédéric is saying
in other
yes.
words, G is an input to the general relativity equation. It's not produced by it, and it's not assumed to be variable, so that you're actually challenging general relativity. Is that correct?
No, I shouldn't. I shouldn't say this like that.
If you're saying that your theory,
roughly, yeah.
If you're saying that your theory, sir, is showing that G is variable and not a constant, you are essentially tearing down lock, stock, and barrel general relativity. And so why would you even talk about general relativity in the first place? You're tearing it down completely.
Okay, so for me, I'm not tearing that. I am not tearing that completely. I'm just fixing something. There was two simple mechanism. When Einstein equation is produced, what is the process? You take Newton's law and you translate it into the framework, the mathematical framework of general relativity. That is a job which is done. I pretend that this is far too simple. You have to do a tougher work, and that's what I am doing inside of relativity. So inside of this mathematical framework of general relativity, I'm doing this demonstration here. Can you see it? I don't know if you can see it.
Yes, small, but, I could.
Okay, it's 7 parts. Yes.
Oh yeah.
It's completely detailed. This is the framework of my demonstration, which is a mathematical demonstration. In the framework of general relativity, it is done by my 50 pages document available on my blog. So you see, I am working in the real core of general relativity. Just why? Just to get something else than Einstein equation. It's not saying that Einstein equation. Just one more thing. It's not saying that Einstein equation is wrong. In some way, Einstein equation is still valid, but with a variable G. That's what I show. That's why I am able to prove with this mathematical demonstration. So therefore, you see, it's a very slight modification of relativity. Very, very slight. It's a, I wrote, it's right also. It's a missing chapter, yes, at the same time. But this missing chapter is not doing so much in relativity. It's just fixing the big problems of gravity, that's all. And some
that's why,
some of them
incidentally, I was a little surprised that you've had such opposition to getting your papers published, because, say, MOND is a modification of existing orthodoxy, but it's not flying in the face of it. So it's being published. Now, many theories, maybe, if I may say, perhaps some of Jim's theories or some of mine or some other people here, are so much contrary to general relativity that they would have no chance of being published. But yours are not so much in opposition. They're just a general modification with, say, G variable. So, but you've had the same experiences we've had in trying to get papers published. So
yes, of course, yes.
Okay.
But yes, it's a good question. It was a good question. Thank you for this question.
So Jim,
yeah, because I don't realize.
Before we move on,
as far as I can see in my own interpretation, if you are stating that the capital G is not a constant but is variable, in my opinion, you're basically discarding the general relativity field equation, which inputs G as a constant. And so, by the way, another question is, how does general relativity predict that G is variable? You say this over and over again, that it's predicted by relativity. How is that done when relativity actually assumes that G is a constant and not variable? It sounds like you have a major departure. This is not a critique of your work. It's trying to put it in context, if you will, sir.
Okay, thank you for this. So I've been presenting this on the last January here in the CNPS meeting. Sorry, why relativity predicts a variable G. It's also available on my blog. You have the video of CNPS of January.
Okay,
on my blog.
We can and then leave that because it's just that's content that's not available today. So you're adding a term to the UG equation. Just a minute. I'll be there in a minute. There's somebody at the door. What, Ian? Take me down and go to somebody else. I have somebody.
Okay, thank you. I will, Jim. Thank you.
Thank you.
Okay, these are the vicissitudes of life. I'm just looking through the comments, which you can see, Frédéric, as well. But you've been concentrating on your own talk. Nick Percival, who unfortunately has gone. He was here at the beginning. Mm-hmm. I don't know if he's in the social media, but he said that Cameron Rebixol argued, and Nick thinks effectively, that the dark matter fudge factor from academia came about because they used Newtonian gravitation incorrectly. Namely, they applied it using the false assumption that the matter in question was distributed with spherical symmetry. However, when you apply it correctly, taking into account the spiral geometry, the answer matches the empirical data to a high degree of precision. Have you any comment on that, or do you understand?
I have to read it, maybe. Sorry.
Yeah, I don't know if you can see that. It's Nick Percival early on in the conference. He's gone now. I wanted to bring him in. I just said, well, we'll have to address that.
Yeah. I have it at 16 and 15 minutes.
Yeah, that's right.
Nick Percival.
That's right.
16.
Correct.
Oh, I have to read it.
Yeah, read it.
I have to read it. Sorry. The huge factor came about. I don't know what is a huge factor. Can you tell me what is a huge factor?
So what we say is dark matter was introduced because the experimental evidence seemed to contradict the existing theories, namely general relativity in some respect. So you just put in, I think it's almost what you called in design or something, that we confuse it with intelligent design, like creationism. But you said changing parameters. So it's like fine tuning. Sorry, you talked about fine tuning. That's exactly what he means. A fudge factor is like a parameter which is just tuned to give you the right result. It's an extraneous fudge
Okay,
factor.
I see. Okay. Factor from the camera because thank you. Because okay. Okay. Okay, so there is a link. There is a link. I will click on the link.
I said to
1 minute.
Nick, but you've just given the link to today's presentation. That's exactly today's conference.
Okay.
So I think that's an error, but he's gone now. But this Cameron Rebensol, you may not have heard of him, but you could have a look at some of that maybe.
But
later.
okay, is it my?
Do you see? So, you have said. I think
what is the link? Is pointing on my.
The link is just to today's conversation. That's just a circular link. Forget about the link.
Oh, okay. Sorry.
You'd have to Google Cameron.
Okay, I see.
No, and I think he's got a lot of information on the web. But I think that you have already said that your theory deals with the anomalous velocity of rotation of the outer arms of spiral nebulae.
Yes, okay.
Yeah, well, he's just saying he's claimed to do this by another means, but you say your theory already does that. So maybe this is just I don't know if it's doing it the same way as you, but he's saying, instead of assuming spherical symmetry, which perhaps the conventional maybe Schwarzschild solution does, you have to modify it to account for spiral geometry. So it might be similar to your ideas, or it might be another way of reaching the same result. I don't know, but you might just note that. I don't think there's anything further we can do in Nick's absence.
I'm afraid they are doing. They take it. I think that they take in account the fact that the galaxy is most of all spiral than 3D. I think this is took in account today by the mainstream. So I don't see any possible explanation with that. But maybe I'm wrong. I'm not.
Yeah, I don't quite see how he's done it.
Sure.
But anyway, you're both in agreement that dark matter is a fudge factor. Maybe that's a new sort of word for you. But that's vernacularly what we might talk about, a parameter which is just put in to be tuned so that you get the right answer. It's a factor which is introduced.
Yes, of course.
It's a fudge.
It's
just messing around. It's not actually, very exact. Okay. So if you have any, at a later stage, view about whether Cameron Rebigsol's ideas are similar to yours or are opposed to, you could let us know, or maybe at a much later stage, talk to us about it. Because we all have our own views. I have particular views about, which I have expressed before, about looking at, say, a spiral nebula and inferring too much from it, because it's really not a composite image. It is a composite number of snapshots, which may not represent a unique time, because the light from different parts of the nebula is reaching us at different times. Some of it has not yet reached us. Some have reached us when the nebula was in a different position and so on. So I'm a little skeptical about these theories. But anyway, so I'm just pointing that out. Let me see now. James, who may be back, I don't know. He said, "What is IGM?" I'm not sure where that came in. I couldn't answer him. IGM.
Oh, sorry. Oh, yes. Intergalactic medium.
Intergalactic medium.
So
yeah. Okay.
It is key importance. It is important in my explanation of the
since we come to
explanation
that,
of,
and you've explained it, thank you. What would your views be on an ether? You know, a sort of a classical ether in intergalactic space, which has certain electromagnetic properties. Do you dismiss that, or do you have
electrodynamic property? Yes, for my research, not for me. For my research, obviously, the ether is space-time deformation. Space-time and space-time deformation are the ether. You see, there is a drift, a slight drift between literature and what I've been just talking about literature on that. That is what I'm saying is that there is an absolute space-time. When you say this in conferences, you cannot say this. You see, it's for historical reasons, of course, and it's a good thing because relativity has been told to students. Everything is relative to each other, etc. So there is no absolute space-time. There is no absolute referential. This is wrong, in fact. Even in the literature, you have an absolute space-time because in the twin paradox, for example, you have one referential, which has a main rule, which is a referential of the twin staying on Earth. So the twin staying on Earth has a prominent role. So there is something absolute there. And when you develop this stuff, you find that really space-time is something absolute. That's what I call the concept of generalized red frame. You have this concept already in general relativity. It is that when you have an object, let's say, so you get an object like this, it moves, and attached to it there is a rest frame. If the model, if I do like this, then the pen will be floating in space. Then it's the old Einstein problem. The pen will be floating in space. The frame which is attached to this pen, is a rest frame. You can generalize this concept of rest frame to any point of space-time. By doing so, you get like what I call an absolute space-time.
Proper time or proper length, proper coordinates. You know, within the rest frame of that object.
Yes, that's it. Yes.
Okay.
Exactly.
Okay.
Yes, exactly. That's the proper attributes.
So, as you say, even in special relativity,
and this is an absolute space-time. This is not exactly behaving as the old ether of the 18th century, for example, the medium of the sun, and etc. But it's not exactly the same. There are some slight differences, but nevertheless, it's something absolute in which there is propagation. Of course, yes. From that point of view, it's an ether. So you see, historically, it was so strong when the Michelson-Morley was explained, so that and relativity, restricted relativity, was so strong for me. Yes, it's the reason why I still try to criticize it. It's so strong. You have to criticize it. You see, it was so strong historically that you couldn't say after that Michelson-Morley. You couldn't talk, even say the word. It was forbidden. You don't have to talk about that unless you will be put out of the church. You know, you will be put out of the church definitively.
It's a new heresy.
Okay, ether is a insult. Is like an insult. You cannot talk about it. You can say the word. You cannot say the word. But I say that already in relativity there is something absolute, which is space-time. When the way I've been describing it 1 minute ago. Yes, of course. Okay. This is the most important thing to do. This is the solution of the main problem of physics. Realizing that there is an absolute space-time in relativity. This is not something
Okay, well,
anecdotic.
that
It
seems
is very,
revolutionary
very
to say
important.
that, because I think the mainstream would deny that, and maybe a lot of dissidents would as well. But anyway, James has made one other point, a trivial point, but he's probably gone. In the equation you gave, with the rho gn, it seemed to be on the numerator and the denominator, rho subscript g n. So he said, well, those would cancel out. Presumably they would, and you'd get a simpler equation. Do you remember that? But you just showed the lot.
Yes.
Yeah, it's not a big point. It's a minor point. I think he's right there. Now, this other gentleman, Ravindra Munda, I had a word with him, and I said, we'll come back to his comments after your talk. But he's gone as well. So I don't know. Anyway, he said, if we apply Newtonian theory properly, now I don't know what he means by that, by assuming disk-type galaxies, well, have they not? I think he means then we get a good galaxy rotation curve by calculation. So just as Nick was talking about spherical symmetry and spiral, he's saying if we use disk galaxies, we don't get any anomaly with the rotation curve.
Did he do the calculations or the simulation for that?
I've no idea. I've never had spoken to this person before. I saw his camera there, and he must have left maybe before the end of your lecture. So I don't know. We'd need to see that. There are so many explanations. We'd need to see that. But
you see, I have an answer to that. I'm sorry, which contradicts it. Sorry, I'm sorry about that, but it contradicts.
No, go ahead.
Because in my simulations, which are the very simple n-body point simulation, I've been showing that Newton's law predicts the structure of a galaxy, which is the red pizza. You remember this ridiculous red pizza I was showing you in the presentation?
Right.
This is what predicts Newton's law with a plane, a two-dimensional representation of a galaxy. And when you replace Newton's law with surrounding, you get everything. You get the most fast rotating bar, the spiral arms, the dwarf galaxies, and you get the ring galaxy all at once.
So this is what I'm interested in, because there are a few theories which seem to be producing the same results as yours, and I'm wondering, is there some commonality between them? That would have to be looked into, perhaps. You might want to look into Cameron Rigbusol's work.
No, that's why. That's why. Yeah, that's why.
If he's looking at the recording, because
that's why I wanted to say before very slowly that you have to specify exactly what is doing your simulations. This is extremely important, because today, I know it, there are big programs of simulations used by the mainstream community, which are doing many things, and at today's time, maybe there are nobody who really knows what is inside the programs. But the end result is quite correct. It goes well. When you compare the result of those simulations with experimental data, it's quite good. The problem is that it's not at all dark matter. It's not at all monde. Maybe I don't know. You have to take time to specify what is doing your program, and the most simple program, the better. You really have to get a very small simple program. And the best one is the n-body one. You don't need more. Look at that. You can have the structure of a galaxy by Newton's law, which is such a ridiculous thing, which is a pizza. When you simulate an n-body problem on the plane, in the surface, so you admit that your galaxy completely plane. Okay, you get this. Now you just replace Newton's law by surrounding, and you get everything. That's all. End of the story. The best thing I've been seeing on that is the situation with one.
If this gentleman, Ravindra...
You need to do simulation because the calculations are too complicated. You need to do simulations.
or anybody else is looking at this recording, I think he could delve a little more into the basis of how you resolve this problem about the spiral arm rotation rate and so on. So really, my last big question would probably be this, and I think you may have talked about this already, maybe last January, but you mentioned a blog. So maybe you could just tell us how to get into that blog, and also if there are any pertinent papers that you have published or either put up on the web, maybe people could look at those. So first of all, how do we get into your blog? Do we just Google Frédéric Lassiaille?
Oh yes, of course.
If we
About the blog,
we'll get a website that you have. I think I've probably did this earlier this year, but I've plain forgotten.
so you go into. It's very easy. So you go to Google and you type my name and surname.
Okay.
And there are no many things. You can see that I'm playing chess.
Oh, really?
You can see that I'm playing chess. Yeah, but very quickly you will see my blog. Okay.
Okay.
And on my blog you can just surf a little bit and you will find everything.
Okay. So if you want to look into theoretical physics, or you want to look at a few chess openings,
don't look at my chess performance. My chess performance are not good. They have been good. But...
Okay.
Sorry for that.
Okay. Well, everything is relative.
So no, it's important.
So it depends.
But the simulation program, for example, the simulation program, the sources. Yes. Sorry.
So is the blog what we would call a one-stop shop? I mean, can people get everything there, or would you like to recommend to us one or two of your publications if you succeeded in getting them published after all the differties you mentioned? So if we go into the web, are there any published papers on that weblog? Any paper, not published, any papers you've written?
No. There are papers which I don't put on the internet because they are either deprecated or just too novel, too much in novelty.
Okay.
So I don't take a risk to say so much nonsense.
Because people have disappeared.
Yes.
I don't know if they're afraid to ask some of these questions, but I don't know why. They've raised very good questions.
I am used to that. I am used to, in my conferences, I bore. I don't know what is going on. Maybe I bore everybody or what.
No, I don't think so.
Everybody goes out.
And by the way, if I may say so, you spoke very clearly today.
It's not your fault, Ian. It's not your fault. It's mine.
It's just that people. I do know that a number of our regulars are in this, and they're making no comments. And actually, we have a number of the subsequent discussions. So, for example, on a Sunday, we have another session dealing with cosmology, which Harry Ricker moderates. But we probably will spend a few minutes on talking about what happened the day before. So they're looking at this, and they're if they miss anything, they look at the recording, which will be available as soon as we stop very shortly. And so the main thing is we can give them some guidelines as to how they can look at this further. Because there's a lot of work you've put in over 20 years or whatever it is, and it's impossible to cover it all in an hour and a bit.
Yeah. For this,
you've done a good job.
Yeah, you have to read the paragraph cosmology in my 2018 article. That's all. It's quite short. It's quite short.
So
where 2018 article about surrounding.
Where is it available?
You have the link in my blog. You have the link in my blog. The easiest way is
the link is in your blog. Okay, that's all we need to know.
Get the link in my blog.
Okay. Now,
yes.
What I normally do,
and it's free. It's open. It's free.
Okay, because it's not the money, but it's just the trouble of registering that people don't like. But that's great. That's excellent. Now, what I normally do is I give the speaker more time. It could be a minute or two, or if you want to speak for 5 minutes, that's fine. We're running out of time now, but just to summarize what you did today and what we did today, and maybe in the light of any of these questions, you may want to add something to say, or you may want to pose a question to us. So I'll give you as much time as you want within, say, 5 minutes or so. The floor will be entirely yours to summarize. And then when you've done that, I'll come back and officially close the meeting. Is that all right, Frédéric? So I'm going again. I'm going to give you the floor just to
thank you very much. Yes.
finish off. So thank you. It's all yours again.
Okay, so I've been working on this research work for more than 2 decades, and today the result of my research work is the following: relativity predicts a variable g. So I am talking about the mathematical part of general relativity and restricted relativity linked together. The mathematical part of it. When I work on it, I found a demonstration which shows that relativity is not at all an anthropocentric constant, but is a variable. So it means that Einstein equation can still be used, of course, but with this new value for g. And there are some interesting things which goes slightly beyond the Einstein equation with this new discovery. So from this relativity, it is easy to construct a gravitational model which reflects exactly the sounding effect which is given by this new relativity. By doing so, the sounding gravitational model solves the most important 10 or less than 10 most important problems of gravitation of today, such as speed profiles, donc Zwicky problem, the Wiggle theorem, cosmology, okay, and bullet cluster, etc., etc. Okay, so that's the main point of today. That was my main point of today, this gravitational model. So yeah, I insist it was a good question I have to answer. This is a work inside of the mathematical framework of relativity. So it does not contradict at all the old relativity. At the contrary, it's a slight modification by inserting something which was missing. So it does not contradict, it enhances, it improves. So I was happy to discuss it with you today. The CNPS organization is for me very much valuable. It's not flattering. It's not. It's right. It's really what I think, because it's free thinking, and it's free criticism. Even if it's not easy, sometimes we make mistakes. I'm the first to do so. But the CNPS philosophy is really mine. Just try, and then maybe you get. Thank you. Thank you very much.
Well, our thanks are due to you, Frédéric, for having taken the considerable trouble of preparing all those slides and explaining to us in such detail what you've been doing for over 20 years. And as I said earlier, it's a valuable addition to our archive, which when accumulated with your January of this year lecture will be there for all time. And we're delighted to have it there. Thank you very much for your kind words. I know you're not just complimenting us, but we're delighted to have thinkers, of all hue, and you'll be very welcome to participate further in our conferences which we hold. And indeed, I hope at some stage in the future come back to us, because when we were talking some time ago, maybe it was some months ago, about the possibility of you giving a further lecture, I was hoping that it would materialize, and indeed it did. And as I say, it's very much complementary to your earlier talk, and it's there for all time. And I would urge a lot of our members to look into your weblog and perhaps come back to us with any further questions in regard to what you have done. I think it's interesting as well. I mean, I've no strong feelings about this. If you've said, well, everything I've said flies in the face of orthodoxy, that's fine with me. And if you said, well, it incorporates a lot of the orthodox views and it just modifies them, that's fine with me as well. I think it's my function as moderator to be totally open to all different views and different complexions and different degrees of opposition to the mainstream. And actually, for my part, if we thought, as we do to a certain extent, that some of your views are timeless, that would be a positive thing, and it would encourage us to publish them. Quite the contrary. So I don't understand how a person said your views are timeless, so we're throwing them out. Just seems absurd. I've been very happy to be in the privileged position of moderating this talk today. Thank you very much for the trouble you've taken, and we hope we'll see more of you. I thank all the participants as well. Sorry, the participants in the through the social media, Facebook and YouTube, were not very active today. You talk a lot among yourselves, and that's fine. I've no problem with that. But you didn't produce much. Maybe it's a bit turgid. It's a bit difficult subject. So when you look at the available information on Frédéric's weblog, you might be more in a position to come back to us, and feel free to do that. And if we're not able to direct you correctly or maybe give you some answer, we will, with Frédéric's permission, pass the questions on to him, and I'm sure he'll be in a position to answer them. So I'm going to close the meeting now, because we're just coming up to the closing time. Thank you very much, everybody. And once again, Frédéric, thank you very much. Merci beaucoup, and good day.